Thanks. I would like to thank the organizers for the opportunity to give a talk here. So I will give a mathematics talk today, but I will first give an overview so that I can justify that it's related to this this program. What we want, this is a joint work with Liang Chang and Xiuhong Ying, Richard. It's an attempt to understand the following picture in the non-semi-simple setting. We want to understand three manifold invariants associated to certain Hopf algebras. Well, in our case, we will consider any finite dimensional Hopf algebra, and we want to understand their categorical invariance. That means whether if you have two Hopf algebras that have equivalent representation category as tensor categories, will these invariant be the same? And then we want to understand whether there are categorical constructions. And we also want to understand if there's any 3D TFT, topological field theory, associated to it. And when H is semi-simple, this picture is complete. So we have, when H is semi-simple, we have the Kuperberg invariant for involutory Hopf algebras, but over C, let's say, this is equivalent to semi-simple. And we know the categorical invariance because we know there's a categorical construction. It is shown that the Kuperberg invariance for three manifolds is equal or up to scaling by dimension of H. The trivial Barrett-Westbury invariant associated to the fusion category H. So because there's a categorical construction, we know that they are categorical invariant. And of course, there's this there's the trivial TFT. Okay. For semi-simple Hopf algebra over C, it's automatic. It's weakly integral to the unitary, and yeah, that kind of thing. Okay. So because nowadays non-semi-simple TFTs are very popular, and we want to get various kinds of TFTs, and there's a close relationship between TFT and the associated manifold invariant, because on the one hand, if you have a TFT of the cobordism to vector space, categorical vector space, you can evaluate closed manifolds to get manifold invariant. On the other hand, given a set of good manifold invariant, we can try to apply the so-called universal construction to see if we have a TFT. So this universal construction basically says you can take, let's say, surfaces and all the three manifolds bounding the surface and use it to generate a very big vector space, and you mod out those dual vectors. So we have a surface. We consider all the manifolds bounding it, and we consider the vectors in this vector space that annihilates all the other kind of vectors. Because when you close it, we get a closed manifold. We can see we can consider when the pairing is 0. So if you happen to get a finite dimensional vector space, then you have a very good chance to get a TFT. So the point is, if we have it is very important to study various kind of manifold invariants, although we are more interested in the TFT. Okay. So what we want to do is to understand this picture for non-semi-simple case. And in this case, there's a natural extension of Kuperberg invariance associated to semi-simple half algebras, but because we have less condition on the half algebra, we compensate by more structure on the manifold. So we want to, so we can get invariance for framed three manifolds. We'll talk about this later. And we don't, yes. So it's just a half algebra that is semi-simple. Half algebra, I will talk about half algebra. So do you know half algebra? Yes. Yes. So it's a finite dimensional algebra which is semi-simple. So it's a direct sum. As an algebra is a direct sum of matrix algebras, and the representation category is a tensor category. It's a rigid tensor category. That's when it's not semi-simple, then the representation category is not a, let's say, not a fusion category. For a semi-simple half algebra, the representation category is a fusion category. But for non-semi-simple, it's not a fusion category. So representations cannot be written as direct sum of simple objects. Yes, yes. An easy example will be, yeah, quantum group at roots of unity. So let's see. Yeah, you have nilpotent things, and yeah. Or we can consider this a very easy one. X squared equals 0, G is group-like, and then xg equals to negative gx. It's a four-dimensional algebra. So this is very easy to check. You have a four-dimensional algebra, and it's a half algebra, meaning you have a co-multiplication from h to h. So this is h. So for x, it's like x plus 1 minus 1 plus x, something like this, plus minus, and then delta g is g tensor g. And then you also have a co-unit that is a one-dimensional representation of the algebra delta x equals 0, delta g equals 1. No, ipso. And so this implements the tensor structure of the representation category. If you consider the category of modules, this gives you the action of the H on the tensor product of modules. And then if you want, of course, we want rigidity. So we have this antipode map S of x is negative xg or something like that. I forgot the exact form. And S of g is g. So this implements the rigidity, the dual structure of modules. Yeah, this is a half algebra. Yeah. This is the Borel. This is UQ, the Borel of the algebra. So yeah. So I just want to write down a concrete thing so that we can think about it. So this, in this case, this is fusion, semi-simple, and then in this case, this is not fusion. Okay. So this case, there can be many indecomposable modules, and yeah. So the representation category is pretty wild. Yeah, for these, for top algebras, or for UQG, I think a lot of things are known, but completely known, I'm not sure.
So do you know what I want to ask? I want to ask this: these representational matrix for operators.
So the paper about any verb and construct, the title is finite tensor category. We try to generalize everything about
No, but this is, no, I'm talking about the non-semi-simple case.
Yeah, not semi-simple. Yeah. It's called a finite tensor category.
Okay, that's why it's called.
Yeah, it's called finite tensor category. No semi-simple.
Yeah, not fusion, just tensor. Yeah.
The whole point is that, as you know, you already said, Joseph thought, the replication is pretty wide. There are uncountable and indecomposable, which is extremely.
Yes.
Yeah, because we recently came up with some examples in PO algebras that also that seem to fall into this.
Yeah, it's definitely more interesting than that method.
Yeah. So with that being said, the category, the representation category is pretty wild, so we don't yet know if there's a categorical construction. Okay, so for such an invariant, but our work is partially resolve the categorical invariance of certain frame 3 manifold. This is our work. Okay. So we prove that for certain frame 3 manifolds, for certain frame 3 manifolds, this invariant is a categorical invariant. That means if you have two equivalent, two half algebras that have equivalent representation category, then they are the same. Yeah.
But representation category equivalent
As tensor categories.
just tensor.
Yeah, tensor categories. Yes, because we for these algebras, the algebra we study are just finite dimensional algebra over arbitrary field, arbitrary half algebra, finite dimensional half algebra over arbitrary field. So
This is a linear tensor.
yeah. Yes. So this, I would say, it's only the very first step of understanding this. Yes.
Without giving state sum construction.
No. That's the thing. So we want to say that. Yeah.
State sum is fully correct.
Well, yeah, categorical construction. We don't know that yet. We want to first study the categorical invariance, and if we establish categorical invariance, then we can say, okay, it's very reasonable to think about how to construct it from categorical construction. So the TFT, well, maybe frame TFT, this is completely unknown. Okay. So the reason that we see such a connection, not only because of this natural generalization of the Kuperberg invariant, and a very central ingredient is the various aspects of the Frobenius-Schur indicator. So I will explain this. This is the only overview. I will explain what I mean by all this. So I will start with algebraic aspects of Frobenius-Schur indicator. Okay. So it's, of course, it's defined by Frobenius and Schur more than a century ago. So I find this in our library. It's in this book. There's only one volume of Frobenius work, and it contains this work. Well, it's the volume 3. I don't know where's volume 1 and volume 2. But in the library, if you're interested, you can. Yes, no. In our little bookshelf in the institute. So there's very limited number of books, but yeah, it contains. No, I don't know. So yeah, it's in German, and in English translation, the title is on real representations of finite groups, Frobenius and Schur. So they're interested in whether a complex given a finite group G, and a priori complex representation, we can find a real form of G, of this representation. That means whether we can find basis of V so that the matrix coefficients are all real numbers. That kind of problem. So for that, of course, they developed the theory of characters from G to C, and it maps G to the trace of rho of G. So this is the matrix, and then this is the trace. Okay, so they define this number associated to a representation that is chi v of this special element in the group algebra. So I wrote 2 here because I will say that if you change this to n, this is still something that is very interesting. And by studying this number, they show that if V is irreducible, then there can only be 3 values of nu2, 1, 0, and -1. And that corresponds to that V can be defined over R, and here V can only be defined over C, and here V is quaternionic. So this actually is the endomorphism algebra of the real group ring of V.
Well, they do more. Let's say it's 0 that the representation is not equivalent to its complement.
Yes, yes, yes. Well, you can derive also from this. Yeah, yeah. And also, well, this definition doesn't depend on simplicity. So if you apply it, so V is defined over, can be defined over R, C, or H.
You were saying that B, if
So maybe.
so, this three cases corresponding to.
Yeah. So if nu2 V is 1, then the endomorphism of the real group ring of V is R. So first lemma tells you it's a division algebra over R, which can be R, C, or H, right? And then when it's 1, it's R. Yeah, yeah.
Physicists learn this is that whenever this indicator is plus or minus 1, it means that the representation is equivalent to.
Yes, self-dual. Yes.
And if it's 0, it's equivalent.
Yes.
And if it's equivalent, then the question is, can you make it completely real or not?
Yes.
And if there are capital places in which this representation only contains real numbers.
Right.
Then
Yes.
is that conjugation.
Yes.
That's
Well, that's exactly what it says. Yes. Yes. Yeah, it's just a language, but yes. Okay. Yeah. So if you apply it to a special representation, the regular representation, well, we say, okay, I consider the regular representation G acting on itself. This is the number that counts the number of solutions number of involutions in the group. Okay, it's very easy from the definition, because chi of the regular representation is either dimension of G or the order of G or 0. Okay, and then what Frobenius-Schur did was they look at a more general equation than this. They want to count the solution of such equations in G. And what they get can be interpreted in modern language as this. I hope you will find this more interesting. Let me see. What is this? Some V in reducible representation of 2V times dimension of V divided by G to the Euler characteristic sigma, where sigma is unorientable surface. Because the pi1 of an unorientable surface has such a presentation, so it has, let's say, k generators, and the only relation is this. Okay, and this should just be k, if this is k here. Well, yeah, unorientable.
Why does formula relate to this equation? I did not.
Oh, so sigma is an orientable surface such that maybe pi1 of sigma has this presentation, X1 generator, K generators. And the relation is, the only relation is this. But they only try to solve such an equation, but it can be interpreted as the number of group homomorphisms. Well, the orientable, for orientable surface, there's also a formula, but that doesn't involve the indicator. And that connects to TFT and was discovered in 1970s, so by Babnik. So
you give a subscript for this indicator, I mean,
yeah, so for n, yeah, we can generalize it to other, yes. Okay. So, well, but I'm not sure whether Frobenius and Schur know the concept of fundamental groups. Yeah.
Yeah, the number on the right is an integer.
Seem to divide it too much. Check the that's not
Let me see. Did I write the negative somewhere?
That would be better.
Maybe I have a negative here. Yeah, let me see.
simple. Z2, so the order characteristic. Oh, maybe.
Yeah, it is. It is an integer, but it's for Z2 is you have one, right? You have one, and then you have two irreducibles. Yes. Yeah, maybe I should. Yeah. Yeah. Yes. Okay. So now there are several generalizations. You can generalize it to from 2 to n, right? And well, that counts the number, let's say, of solutions of g to the n equals to e. There are other properties that you can say. But the next step is to generalize beyond finite groups. So we consider half algebras. So I have already written some elements about a half algebra. It's an algebra that has this structure map satisfying certain conditions, and the actual thing that we want is representation category of H is let's see, rigid. It's a tensor category. It's a rigid monoidal category, linear. Okay. And so, for example, group algebra are, of course, half algebras. We always have.
I think we don't know if this category is always given. We only know it's rigid.
For non-semi-simple, there are examples where this is not pivotal, even for finite dimensional, I think. Yeah, non-semi-simple. For semi-simple, we know it's always spherical. Yeah, but for non-semi-simple, there are examples where it's not pivotal. Yeah. We can easily check that the antipode generalize the inverse map. In the half algebra, this is the diagonal map. Okay. And I want to introduce some notations, because when I try to write down the Kuperberg invariant, I will need this. So if I have X in H, and I take its image under coproduct, it's an element in H, tensor H. It's in general, if you pick a basis, it's a sum of basis elements. But sometimes we only care about the position, the tensor components. So we just label the component, the first component, the second component. there's a big sum over certain things that we will omit. This is just a notation. This is called Swiller's notation. This notation is tailored for complicated computations in Hopf algebra. So just first component, second component, remember there's a sum. That's all we want. And with this, we can define the Swidler power, which is a map from H to H. Well, what is this M? It's related to how we define the map. So when M is 0, it's the co-unit, and then when M is larger than or equal to 1, we just take the co-product and then multiply them all together. Okay? So for example, I will always omit the summation. So for example, let's take an example. I take the group algebra. I can take this element. I call this lambda. Okay, so I perform delta. By linearity is we can just perform it to each g, so it's G tensor G. Okay, but we cannot say that x1 is sum over G. It's not a pure tensor. It's just it's a sum of pure tensors. Okay, so this is I think you can just call it a placeholder. So it doesn't really mean that it's something tensor something. There's a sum in it. So for example, this is a sum of pure tensors. Okay. And let's see, P m of lambda is 1 over G sum over G to the m for m larger than or equal to 1. We just multiply them together. Extend by linearity. So this multiplication, of course, is a linear map. And this element, you can see it's an invariant vector under group multiplication. So it's a very special element. So for Hopf algebras, there's the notion of integrals. That is an element in H such that x lambda is, so lambda is a vector that implements the representation from H to C, any x. So for example, this lambda is such a special element. Well, if H is finite dimensional, there's always a one-dimensional space spanned by the left integrals. Of course, you can define right integrals, and the space may not be the same. Okay, but we will not go to the technical details there. And we also have this notion. So H is a Hopf algebra, then the dual, which is just a let's see, C, H to C, linear functionals, we can change it to other fields, is also a Hopf algebra. And we call integrals, we can consider integral here. We give it a notation because we will use it later. So for group algebra, we can take this to be, let's see, the delta function the unit. Okay, and then with this setup, we can state the general definition of a Frobenius-Schur indicator for semi-simple half algebras. Linchenko and Montgomery defined for semi-simple, of course, finite dimensional H defined over complex number, and for any V in a rep of H modules, this nu n of V is defined to be chi. We first take an integral lambda in H such that epsilon lambda equals 1. We can normalize the integral because, like I said, there's a one-dimensional space of it. But you can do this only when H is semi-simple. Okay, so then nu n of V is defined to be chi V of P n of lambda. Okay. So this is exactly the generalization of group algebra there. So this generalized this element. The chi, of course, is the trace of representation. It's also a direct generalization. I don't know.
Yeah, I mean,
Yes.
I know. He was student of Yilong Wang. I'm not sure if he's.
Well, the reason I'm asking is I know in my paper, Richard wrote a history of it.
Okay. Well, yeah, yeah. Well, later. So they did it around 2000, and Samhauser, Kashina, Samhauser. That's my next bullet point. I see. Yeah. So Kashina, Samhauser, and Zhu showed that, well, they also generalized it to in a more general setting, but they mainly used the property of this thus defined indicators. In particular, they show that this is equal to the trace of the antipode composed with the n-1th. The n-1th scalar power, and it also equals to lambda s p n of lambda by for semi-simple, H equals to semi-simple. So then you can drop the s, but this is very important for us to generalize to a non-semi-simple case. So by Radford trace formula, we also have this. So this is the form that is inspiring to us, because if we only take the character, we won't be able to really generalize it to non-semi-simple half algebras. But these are universal. You just have an operator defined on the algebra, you take the trace. And then you can try to ask whether they are invariants of the category. Okay, and this is also universal, so lambda s. Although, like I said, if you are not semi-simple, you will not be able to take this kind of normalization, but this, you can always take this kind of normalization. Okay, you can always normalize your integral and co-integral, so in the functionals of H to be 1. Yes. In particular, they also can write it as the trace of some operators that it's a little more complicated. Yes, a little more complicated. And it turns out that their formula is simply the formula for Kuperberg invariant that I wrote. Yeah, that will tell. Yeah. Of course, these are used to study properties of half algebras, like invariants such as the exponent and stuff. As is the antipode. Yes. Yes. Okay, and then, well, I will skip several developments for C star half algebras by Fuchs et al. And directly tell about the categorical generalization. Okay, so and Schoenberg, because their picture is very important. Generalize it to Frobenius-Schur indicator for linear pivotal monoidal category. You don't need semi-simplicity. You don't even need abelianism. You just need, yeah.
H was coming from a group G, and then the second line is where it's more generally H is just a semi-simple half algebra.
Yes.
So chi B was the trace you had.
So you can, of course, a module for H can be a H2 endomorphism of V, and then you can also take the element of X and take its trace. Also, that's the chi V of X in H. You can also consider such trace functions and call it the character of the half algebra, of a representation of a half algebra. We can look at this in general. Even non-semi-simple things we can for non-semi-simple H we can also consider characters of representations. That's also fine. But sometimes they don't tell you the full story of the full information of the representation.
What was generalized?
Oh, this is not the example. This is another bullet point. I should make it clear. So this is a separate example. So Lenchenko and Montgomery extend the definition of Frobenius-Schur indicator for general semi-simple half algebra. And their definition is given a semi-simple half algebra, you take a normalized integral. That's you can only do that in semi-simple case. This relies on semi-simplicity. Okay, and then you consider characters of representations which does not depend on semi-simplicity. You can always consider this number, but for semi-simple ones, you can define this number, and they have similar properties as the indicators for finite representation of finite groups. So that's the logic here. And then it is so their property were further explored by these three people, and they show that you can write it as the trace of something. Also, you can use the co-integral to write it down, so that we can a priori we can avoid this. Okay, so this heavily relies on semi-simplicity, but these two things does not require semi-simplicity. So we can look at them and study their property for non-semi-simple half algebra. Okay, good. So in this case, I have a category C, and I have an object. I can consider this Helm space from one. Well, it's a pivotal monoidal category. But let's call the pivotal structure J from V to V double star. It's a monoidal natural transformation from the identity functor to the double dual functor. Okay, so this is a pivotal structure. And we can consider the Helm space 1 to V tensor n. Well, this is a vector space. It's a vector space. Let's see over K. I don't need But for this, I don't even need C. Okay, so now I can consider a linear transformation for an integer n. I define a linear transformation from this home space to itself, given by, I will use a little graphical calculus. I have a morphism from the tensor unit. I read from top to bottom, from tensor unit to V tensor itself n times. So this represents a morphism. Well, where does it go? It goes to this morphism. So this is V, so n minus 1 times. And so here we have V star. We have the evaluation here. We have co-evaluation of V star, so we should have V double star here. And that's why we need the pivotality. So we can use the J inverse of V to change it to V, so we get back to our space. So this is a linear map on linear endomorphism on a finite dimensional vector space. And now we can take its trace. So the definition of n and Schoenberg of the nth indicator is just the trace, k-linear trace of this linear operator. Okay. Any question about this? Because this picture is for n equals 2, it's so I have V and V, right? From 1 to, so let's take a fusion category, right? Let's see example. Let's see V be a, let's just take representation of G. Okay. So I have, I consider a linear map, G equivalent linear map from C to V tensor V, right? The G equivalent. And we know that if, for n equals 2, if V is not self-dual, if V is not equivalent to its conjugate, then there's no such map. The space is 0. Okay, so then we take the trace on a 0 space, we get 0. So this coincides with the 0 result. And also, so V is simple, let's see. And if V is, well, self-dual, well, there's a one-dimensional vector space of such map. Then we map it to, well, for example, we can just use the co-evaluation as a, strictly speaking, not the co-evaluation, but let's draw it like a co-evaluation. Okay, and then we take the map it to this and consider the pivotal structure here. Okay, but yeah, this is actual co-evaluation. Let me not write it as co-evaluation. This is just the basis for 1 to V tensor V. So you see the difference. Because if you draw it as a co-evaluation, you may say, okay, I have a rigidity, I can resolve it, but it's really not the case. Okay, there can be a -1 going on. So, well, yeah, it's just a composition of from 1 to co-evaluation of V star to V star tensor V double star, and then 1 compose F compose 1, so it's V star tensor V tensor N tensor V double star, and then you take the evaluation of V and then identity on the other, so you get V tensor N minus 1 to V double star, and you compose with the inverse of the pivotal structure, you get back to V tensor N. This is the map. And we take the trace of this. well, if you apply it to group or to half algebra, we can write down very explicitly and recover the equation here. Well, it's elementary, but it's not completely trivial, so I will prefer not to do it here. But the point is, when we apply this construction to, let's say, for a representation of finite groups over C, we will recover this equation. Okay? And you can see it's a trace. The character is a trace. So it's just a matter of interpretation. Frobenius-Schur indicator is also a trace. Okay. And if we apply the construction for if C is fusion, is pivotal fusion, we can take a dual basis. Let's see, I alpha in the inclusion of n and pi alpha in also in this space. Okay. So that yeah, so by semi-simplicity, we have a dual basis for this spaces. Then nu n of v is, well, we take trace O of this morphism space. We take a basis, then we just apply it. So graphical calculus says I can take the I alpha. I'll draw this picture. This is pi alpha. I just sum over basis and dual basis. Okay. Well, here we should add something, but general category theory tells you that you can strictify it, so you really don't need to draw it. Okay. So this picture is important. Okay. What about, so far we have talked about semi-simple case, right? For non-semi-simple case, we do have this, but it's not really what we are heading to, because we want to use it apply it to Hopf algebras. What happens now semi-simple Hopf algebra? And it was shown that this is Katrina, Montgomery, and showed that this number, this trace, which can be defined even when H is non-semi-simple, this number is a categorical invariant. So let's write it as a prime H trace of S composed, antipode composed spherular power. Well, it can also be written as this is a categorical invariant. For any finite dimensional Hopf algebra. Okay. And this is very good because in the study of Hopf algebras, for algebras, we of course want more and more categorical invariant to study the property of the category representation of categories, category of representations. Then well-known categorical invariants include the dimension, the exponent, some trace of powers of the antipode, but this gives another family. So of course we want more, and that's where we are heading to.
Same thing here. You can also I'm asking, is this formula applied to indecomposed?
I don't think so. Yeah, it's I think it's a very global information, and if once you're not semi-simple, the trace cannot give you other information because of the nilpotent part. That's my understanding.
Well, this is the regular.
Yes, this is a regular trace.
Not necessarily zero.
No, yeah. Maybe it can extract some semi-simple part when you have this. I think mainly. Yeah.
This is
Yeah.
matrix quantum groups.
Matrix quantum groups. What are they?
I don't know what way to point.
Yeah. Well, what are?
It's like the analog of an exponential of generators. So quantum groups typically you write it down in terms of generators. But there's some kind of a notion of an exponential of these things. Matrix quantum groups, and like you have Lie algebras and Lie groups. Matrix quantum group like those. Yeah, exactly.
What was that?
Like Voronezh quantum groups, like local quantum.
Ah, locally compact quantum. Yeah. Well, as long as it's half algebra, it can be applied. Yeah. Yeah.
So do I remember correctly that like the way it's proved that this is invariant is that one goes to the Drinfeld double of H, and then this quantity is a trace of the Drinfeld isomorphism?
No, that's for exponent. That was the proof for the exponent. For this, we really use the gauge transformation. We just direct computation. Gauge transformation, the two co-cycle twist. So so two half algebras. Let me write it down. So how they prove it? So H.
Do you know roughly when this is proven?
2010, something like that. Yeah. I forgot. I'll check later. So we have a tensor equivalence if and only if there exists an invertible element in the H tensor H satisfying, let me see, giving the identity functor of rep H a monoidal structure. So we can unpack this definition of the monoidal structure of the identity functor.
Yeah, it also involves like some anamorphism, but that's like independent categorical description of this quantity.
This Shimizu has some. It can be realized as some. Also, the trace. No, not involving the double. I don't think so. It involves. It's similar to this rotation thing, but you can write it down in categorical terms. Shimizu did that.
But for rotation, you need Levatard, right? For this to compute the trace. Here you don't assume that.
No. So that's why you just directly add S square whenever you need it. Yeah, when you rotate, you have S square, but in terms of half algebras, you can just say I have X square somewhere, and then it's a transformation on morphism space.
I mean, what puzzles me is that this is done for half algebras, not for tensor K.
No. So it also puzzles me. I don't know what the categorical construction is, but and we want to generalize this, well, we want to ask whether the generalizations are categorical invariants, and then if they are, probably there's a very good categorical construction behind all of this. This quantity. To Kuperberg invariant. I want to write this as the Kuperberg invariant of some frame 3 manifolds, and I want to say that we can look at other Kuperberg invariants of Kuperberg invariants of other 3 manifolds. We can also have categorical invariant.
Well, you can do it, then that's Kuperberg invariant can be related to the double. The Kuperberg invariant is not a double.
Well, even for, well, Yes. Yes. Yeah, for semi-simple case, it's exactly double, yes.
If you can write it, you don't Kuperberg invariant.
Yes, and well, there's the framing issue, right?
There's always a framing issue.
Modulo framing issue, yeah, we can relate it to things in the double, yeah.
Because Kuperberg invariant is the Prof invariant.
Yeah. Oh, I almost have no time. So let me just give you the punchline then. So with all this, yes. Huh? Okay, okay.
I don't think you can worry about time. People can just eat.
Okay. So what we really want to say about the the topological aspect, yes, okay, is the we want to relate this to the Kuperberg invariant.
By the way, maybe I can make a comment about
Yeah, sure.
I think this is the deepest quality of algebra, non-simple alpha algebra. This is the incredible direction by Kuperberg. Where few people do what it means.
So I will not start with the most general invariant for frame manifolds. I will first talk about if given a semi-simple finite dimensional half algebra H, let's say over C, in this very simple case, we get a pairing with H from homeomorphism classes of closed oriented three manifolds to complex numbers. Okay, so M is assigned to a number. Yeah. And this is done by a very algorithmic way. Okay. So first of all, we start with a combinatorial description of three manifolds. That is called the Higgs diagram. Okay, so what's this diagram really says? Do we know what the Higgs diagram is? Okay, I will draw pictures. If we all know what the Higgs diagram is, I will not draw the picture, but I like the pictures I designed. So okay, so Higgs diagram. So first of all, we start with the fact that any three manifold can be decomposed into the identifying two handle bodies of genus G along their boundary. So I will explain what I mean. This is stands for genus G handle body. It's just a connected sum of solid tori. So I have solid torus and glue another one. What I do is I fill a surface of genus G. That's all I do. This is called a handle body. Because why it's called a handle body? Because it is a ball attached with solid handles. It can be viewed as this. Okay, so it's called a handle body, and its boundary is a surface of genus G. Okay, so if I know, so how do we do that? So this decomposition theorem seems like a very big thing, but it's actually very important, very simple. What we do is just thicken the one skeleton of a triangulation of M? Well, of course, you have to assume the existence of triangulation, which is, and that is the hard part to me. Okay, but once we assume that there is always a triangulation for three manifolds, there will be, you can thicken the one skeleton and get a two handle bodies. And how do we do that? The picture is like this. I can take a tetrahedron. Okay. Well, many tetrahedrons that triangulate my manifold. I just the one skeleton are the vertices and edges. I thicken it. That means I take the tubular neighborhood of this. Okay, so if you want, you can say, okay, I can say, attach this, maybe some cosmetic. Okay, so then you can see it's a solid thing. And well, you can shrink these two balls together, right? You can shrink all the balls together so that I have a very big ball at the end. And so once we shrink this, this becomes a handle that's attached to this ball. So I have a handle, I have a handle, I have a big handle body. So this is one of the handle body. The other one is the dual, the Poincare dual, because the two skeleton and the three skeleton so I have a dual one. Okay, so I have two handle bodies. I put them together, I get M. So the splitting is easy. So, but the real information is encoded in this map then, the identification on the boundary. Okay, so well, how to characterize such a map? So F is then determined by its action on curves. Well, curves on surfaces basically carries all the information of the surface. If you choose the correct system of curves, then you can determine F. For example, I can just, in particular, I only need to know the image of the meridian of the handles. Okay, so where are they? They are here. Or here. Okay, so alternatively, we can think about this picture. Okay, I have the meridian here, the meridian here. Once I know where to map this to, right, I can cut my handle body along this. Okay, I will get something like this. Once I cut this, I will get a ball. So the only non-trivial thing happens at the neighborhood of a meridian. Once I know where to map the meridians, the rest of the gluing is just a ball. And up to homotopy, there's only one way to glue a ball. So that means to encode the F, I only need to, so if this surface is of genus G, I just need two sets of G curves. Okay, one set is your chosen meridian, the other set is their image. Okay, of course they have to satisfy certain properties. I will leave this picture here. I will erase this. Okay, now our task to describe this homeomorphism is to describe curves on surfaces. Okay, so, well, we can, for example, draw a surface like this. And okay, I have, well, meridian for one handle body and longitude for the other. So, well, I take the dual picture actually, but so I can have something like this. Okay, 2 sets of curves, genus 1. So I need 1 meridian from the for the complement actually in the picture, because in this way my other picture will become better. But we will compare. Okay, so 2 curves, 1 curve and their image. Okay. And well, for higher genus curves, you know, you have to run around and draw very complicated thing. And then you realize that we really don't need this part. Okay, because in the handle body, where is it? In the handle body, I can just get rid of 1 point. So in the surface of boundary of a handle body, okay, I take out a point, I will get like a plane, and then handles attached to the plane. So let me draw that picture. So I will have a plane, and I will have a handle attached to the plane, and I will have 2 sets of curves. This curve, and another curve that goes like something like this. Okay, I push it to the plane, and then you realize you don't even need this handle because you can push everything down, so that what we have is something like this. So everything just goes straight up. So I can push this down, so this winding happens on the plane. And then like this. I push everything down on the plane. Now I have a planar picture. So on this plane, I have 2 circles giving me the position of the handle. Okay, I have a, now I only have to remember that this point is identified with this point because I remember there's a handle going up. So I directly identify these 2 points, and that corresponds to this. Now I have a red point here. I have a red point also here. Okay, so I can go like this, go around twice, and I go in, and there's a handle. I go from here to here. I connect these 2. Okay, so it's just the position of handle and the identification of points. That's all that we have to memorize. Now, this is what nowadays people use for to call Higgs diagram. This is a commonly used way to represent Higgs diagram. But of course, the position of the handle you can change. And if you read the first, if you look at the first Higgs diagram in history, I think it's Poincaré who described this homology sphere. And he put his handles like this, where this and this are identified, and this are identified. So you have freedom to choose. This is the way we choose. Okay, and well, this is the one we want to use. But remember, this choice of point of view is arbitrary. We can so this by no means canonical. 3 manifold has many Higgs diagrams. So remember, if you can consider this, I can also consider its complement, because the complement is also a torus. Okay, so now on the complement, okay, where is the yellow circle? The yellow circle is here, because it goes around this. Okay, I cut it here. Now where is the red curve? The red curve is like this, and this is why we keep this here. So it look very similar. Okay, so I want to use this to somehow convince you that it is reasonable to connect the Frobenius-Schur indicator and the Kuperberg invariant, at least pictorially. Okay. So now, given I will keep this. Maybe keep this here. Combinatorial description of three manifolds. Okay. Now, then we can implement an algorithm. Okay, so given pick a diagram, let's say gamma of a three manifold. Okay, well, I have two sets of curves, right? By arbitrary choice, I call one set upper curve. Well, we will see there are a lot of arbitrary choice. At the end, we have to show that it doesn't depend on the choice. Okay, well, I don't have to show, Kuperberg already showed, but, and I call the other set lower curves. This is for the sake of implementing the algorithm. Okay, for each curve, I pick arbitrarily orientation and starting point. Well, or you can call it a parameterization, whatever you want. Okay, you just pick arbitrarily. So this is the setup. So the first step is to each lower curve. Okay. Assign. Well, this is just symbolically. Okay. Assign the a copy of the integral labeled by L. I put it on the superscript. I label it by L. Okay. So this is the so here we have lambda integrals, pair of normalized integrals. Okay. Special elements. It doesn't really matter if you don't go to technical details. They're just two special elements in H and H star. Okay. I give a copy of this, and as I go along L at the ith intersection point, assign also symbolically Li. Okay, so at the end we will perform. So we actually will have to perform coproduct several times. To each of the integral. Okay, so we will have a big tensor element in the big tensor product of H. But we just symbolically assign this, the ith tensor component of the coproduct of this special element. Okay, so let me, sorry, with upper curve. Yes, exactly. Yes. Yes, because they're meridians, I don't want them to be intersecting. So, yes. Intersection points with upper curve, yes. So let me give, I can order the points because I have already taken a starting point. Okay, so let's say my lower curve is here, and it intersects maybe in general with several upper curves. And okay, I may have orientation like this, and like this, and like this. Okay, so let's say this is U prime, maybe different upper curves. And then, well, if this is the ith intersection along starting point of this lower curve, if this is the ith point, I put Li I here. So if this is the I plus first, I plus 1. So at the end, when we write down a formula, this will make sense. But now they're just symbols, right? And well, because there's this different kind, there are two different kinds of intersection between upper and lower curve. We also want to adjust by the power of, okay, probably I directly write here, maybe. Add s to the star to lambda L I, where star equals to 0 if we have one of the configuration. So this is a lower curve, this is upper curve. And S is 1 if we have this configuration. Okay, the reason we don't have higher power of the antipode is for semi-simple half algebra over C. S squared is identity. Okay, so this is for semi-simple. For non-semi-simple, we will have other powers of S. Okay. No, we get to choose arbitrarily, and then we have to show that. Well, of course, you have to show that it's independent of your arbitrary choice, and that's part of the proof of Kuperberg's paper. Okay, so now we just arbitrarily choose. Okay, and then for example, for this one, I will have S1 S here. For this one, I will have no S. So S to 0 is identity. Okay, put it here. Okay, and then you go along. This is 3, 4. Go along each upper curve and multiply. Maybe not multiply. Concatenate these symbols at intersection points with lower curves. Okay, so well, I have a, now I go along each upper curve. Okay. Well, I may intersect with several lower curves. And here I have a symbol here, some power L something here. And here I have some power, some L prime, and some other label here. I just concatenate them. Okay. So then I will get a product of power, the Lth, and something here. They can all change. Okay, they may not be ordered. So really, this Hegel diagram gives you a permutation on these labels, and you multiply them together. And at the end, we compute put it up. So finally, this Kuperberg invariant. At this point, I can only see that for this gamma plus choices for H is determined maybe I call it maybe I call this a word for the upper curve. Okay. So I can take lambda to the g, evaluate at W of U1 tensor W of U2 tensor W of UG. So this is a word that's can be viewed as an element in H tensor itself. So by itself, it's not an element in H, right? It's just a symbol. But when we write them all together, and remember there's a big sum here, it makes sense to view this whole thing as something in H tensor itself G times. And then we can evaluate it. Okay. And well, of course, one has to show that it's the theorem of Kuperberg says is independent of the choice of gamma and other choices. So we can write this as Kuperberg invariant of M and H. Okay. Now, if we apply the algorithm to this diagram, let's see. Maybe here. I will have, so I start from here, okay? So this, I assign lambda 1, so there's only one lambda. So this is lambda 1, this is lambda 2. And what's this? So this is S here. There is, what's this? Yeah, there's also an S here. Let me see. Yes. So I think this is 0. This is 1. Yeah. And this you can also change. As long as you change consistently, you will also get the same thing because it corresponds to the change of orientation. And then I just multiply them together. I evaluate. Okay. And then this equals to lambda S. S is a algebra anti-homomorphism, so lambda 2, lambda 1. But in semi-simple Hopf algebras, this equals to this. And this equals to lambda S P2 of lambda. Did I leave it? Unfortunately, no, but well. It's a, yeah, it's a length space.
But it's a genus 2 equals space.
No, genus 1. So this pair, one pair corresponds to one handle. Yes. Yeah. So this is IP3 actually. Yeah. 2 1. L 2 1. So yeah. Yeah. So the algorithm is probably clear, right? And now we get a familiar equality like before. So actually, well, this corresponds to also a choice of orientation. You can also say the same manifold can be maybe here. can be also represented in this way. So they have different orientation, but that's fine. So the point is, a manifold that looks like this, it has a genus 1 splitting. A manifold has a genus 1 Higgs splitting is called a length space. We can define it. Let me write it down here. Length space. 3 manifolds admitting genus 1 Higgs diagram, let's say. Higgs diagram or Higgs splitting, because this diagram is the diagram of the splitting. Okay. And well, we have a genus 1 splitting, and we want to describe is of course described by a curve on the torus, and the curve on the torus can be really determined by its slope. Okay, so it's determined by a pair of integers, the number you go around meridian and the number you go around longitude. And so this such a space is denoted by Lnk. And a typical Higgs diagram for Ln1 is just, well, we can draw it this way or the other way around. So n times, n intersection points. Okay. So this is Ln1. Well, you have 2, then you have 2 things going around, and then there's some division algorithm that you have to do. So the point is, yeah, it's easy to show that Kuperberg invariant of Ln1 of H equals to lambda S P n lambda equals to nu n prime of H. Well, nu n of H for H semi-simple. Okay. And well, there's more to it, right? There's well. Yeah. Okay. Yes. 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 Okay. Let me read my result. Yes. I took too long. Sorry. So for non-semi-simple of algebras, Kuperberg defined invariant for framed 3 manifolds. So it's a 3 manifold with a choice of a framing at each point and consistently and consistent with the orientation. And he also gave a combinatorial description of this, of such a frame 3 manifolds, and an algorithm to compute the invariant. Basically, framing just give additional decoration on the Higgs diagram, and according to the additional decoration, we can compute a number. Basically, we just change the way we assign the power of S, and also we have to twist by some special group-like elements, but that's technical details. But the basic algorithm are the same. So you go along lower curve, assign things, and then you go along upper curve and multiply things. Okay. So our theorem is the following. So for any finite dimensional half algebra over any field, okay, and any framing the length space, the Kuperberg invariant, any framing F H is a categorical invariant. And in fact, we also find the categorical invariant for a large number of for some genus 2 three manifolds. Okay, so including the homology sphere, and so we think it's true in general, but for that I think we need other techniques to do. Okay, yeah, that's basically our result. But to describe this, I need to introduce the definition of Kuperberg invariant. Okay, that's it. Thank you.
In a similar sense, do you know in general LM is the information at all? So just reduce
Nothing new in the sense that it can always be computed by the modular data. If you the semi-simple case, right?
Yeah.
So the modular data of the double. Yeah, nothing really new. Yeah. Yeah, there's something new. But what's essentially new is the zero part. Sometimes you get zero for certain manifolds, and it's really strange to have them. You don't see this in semi-simple case.
So I have a defined new modular data.
New modular data. We have to.
It's a little complicated. So you have to take this Friedman ideal, and the key matrix is a beautiful thing to Lama change the center of any of the representation of L2Z and try to take an ideal in wherever subspace. And there is a canonical choice of base. I think the won't be surprised too. But a nice space.
Yes.
But you're saying that in the semi-simple case is determined by modular data of what? Of the center of the case?
Yes. The center. Yes.
So it cannot be modular.
Yeah. So I take a semi-simple half algebra. It may not be modular. Yeah.
Modular data itself is not.
No. And also this space is just the genus 1 three manifold. It's not all.
So the invariant determined by modular data or just by the center itself?
Modular. Modular data. We don't need all the information about the center to determine this invariance. But to determine other invariants, we need the center, I think.
But then it suggests that it should be, because it's determined by the modular data of the center, that it should be invariant of Marita class of categories. So for instance, H and H star should give the same.
Yeah, yes. Actually, so we wrote a sequence of paper with colleagues at BIMS giving another understanding of Derive-Zero and Rashtigan-Derive TQFTs. We call that ultrafolds, right? Yeah, that paper with Zheng Wei. No new results, but it's a helpful point of view. From that point of view, it's very easy to see that such things are Morita equivalent, Morita invariant. So because we can,
But then
yeah.
That
This is for semi-simple, yeah. This is for non-semi-simple. Arbitrary finite dimensional half algebra over arbitrary field. That's what we, really extend. Yeah, because previously the result, including Zhenghans and Liang's and Cui's result there for factorizable ribbon, but this doesn't really have any. Yeah.
What Kuperberg invariant have the tensor G in its definition?
So this is it's in the process of the definition, but at the end, we have something. So for each upper curve, we have each upper curve corresponds to a component of G of H. So we have this. At the end, we use this H star to the G. So we use this element here to evaluate each component, so we get a number at the end. Yeah. So in the middle, each upper curve gives you a word in a copy of H, and then at the end we evaluate them out to just get a number. At the end, the Kuperberg invariant is a number. No, the number for each genus, the formula involves the genus, right? So for example, here the genus is 1. We only use one copy of the special functional to evaluate one copy of a word. If you have a genus 2 figure splitting Higgs diagram, then you would have something like lambda acting evaluating at certain words times lambda evaluating at certain words. So, or written in another way, so lambda tensor lambda evaluating at something tensor something. This is in H, this is in H, something like this. But at the end, what you will get is in the ground field K. Oh, yeah, it is the number. Oh, okay, you're asking about this. The G is the number of yellow curves, and it also equals to the number of red curves. Yeah. Okay, thank you.